Let's do an example of an overdamped case to show how we can come up with a total response for this parallel RLC circuit. Our first step is to determine the dampening. Determine the dampening. By that, we need to determine whether the value under the radical, the square root of alpha squared minus omega naught squared, we need to determine whether that value under the radical is positive, negative, or equal to 0. So alpha squared, well, alpha is equal to 1 over 2 RC for the parallel case, which is equal to 1 over 2 times R, which we've been told is 200, times C, which is 200 nanofarads, or 200 times 10 to the minus 9th. Alpha then turns out to equal 12,500. Now, since we're going to need it, while you've got 12,500 in your calculator, let's go ahead and calculate alpha squared, which turns out to be 1.5625 times 10 to the 8th. So alpha squared is that. Omega naught squared is equal to 1 over L times C, which is equal to 1 over L, which is 0.05, 50 millihenries. C, once again, is 200 times 10 to the minus 9th. And omega naught squared then turns out to equal 1 times 10 to the 8th. So we have alpha squared is 1.5625 times 10 to the 8th, which is greater than 1 times 10 to the 8th. Therefore, alpha squared is greater than omega naught squared, and we have an overdamped circuit. Now, what are the values of S1 and S2? S1 is equal to negative alpha, which is negative 12,500. Let's see, let's do S1 and S2. Negative 12,500 plus or minus the square root of 12,500 squared, which we know is 1.5625 times 10 to the 8th, minus omega naught squared, which we know to be 1 times 10 to the 8th. When you evaluate that, you get S1 is equal to negative 12,500 plus the square root of that, which gives us S1 equaling negative 5,000, and S2 then equals negative 12,000 minus the square root of that quantity, which turns out to be a negative 20,000. So we've determined the dampening. It's overdamped. We know then that the voltage will be of this form. We now know S1 and S2. We can then write V of t is equal to A1 e to the S1, which is minus 5,000 t, plus A2 e to the minus 20,000, or S2 t. And all we have left to do is evaluate A1 and A2 from the initial conditions, which were given to be the initial voltage is 12 volts, and the initial current is 30 milliamps. Alrighty. From the previous video, we saw that we can evaluate this at 0 plus, which then gives us A1 plus A2, and of course that's going to equal 12 volts. So our first equation is pretty easy to get. The initial voltage on the capacitor, the initial voltage across the capacitor, which is the voltage across all three of those terms, or all three of those devices, is 12 volts, and that's got to equal A1 plus A2, or A1 plus A2 has to equal 12 volts. Now, the second equation comes from differentiating this and evaluating the derivative at t equals 0. So, dV dt evaluated at t equals 0 plus is equal to A1 S1. S1 we found to be a minus 5,000, plus A2 S2. S2 was found to be a negative 20,000. And we know then that those two terms must equal I sub c at 0 plus divided by the capacitance. Now, how do we determine what I sub c at 0 plus was? As you'll recall, we did a Kcl equation at that node, and we had then I sub r at 0 plus I sub c at 0 plus I sub l at 0 plus must equal 0. I sub r at 0 plus is just the initial voltage of 12 volts divided by the resistance of 200 ohms, plus I sub c at 0 plus, which is what we're looking for, plus I sub l at 0 plus, which is 0.03 amps or 30 milliamps. The sum of those three things must equal 0. Solving for I sub c at 0 plus, we get that is equal to a negative 0.09 amps, and thus I sub c at 0 plus divided by c is equal to negative 0.09 divided by c, which was 200 times 10 to the minus 9th, and that equals negative 4.5 times 10 to the 5th. So we've got one equation right here, A1 plus A2 equals 12, and our second equation, let's just write it right here, negative 5,000 A1 minus 20,000 A2 is equal to I sub c of 0 plus divided by c, which we found to be negative 4.5 times 10 to the 5th. So there's our second equation. Solving those two equations for A1 and A2, we get that A1 is equal to negative 14. A2, it turns out, is equal to a positive 26. And we now can write then our final equation that we've been looking for, V as a function of t, is equal to A1, which is negative 14, e to the minus 5,000 t, plus A2, 26, e to the minus 20,000 t. A quick consistency check is to verify that this satisfies the initial condition. At t equals 0, we have positive 26 minus 14 is the positive 12 volts that we knew was our initial condition. So let's rewrite our V of t here is equal to negative 14 e to the minus 5,000 t plus 26 e to the minus 20,000 t, and show that once we know the voltage across these, we can determine expressions for each of the currents here. The current through the resistor, I sub r as a function of t, will just be V of t divided by the resistance r, or negative 14 e to the minus 5,000 t plus 26 e to the minus 20, that's a 20,000 t, divided by 200. And that equals negative 0.07 e to the minus 5,000 t plus 0.13 e to the minus 20,000 t. So the current through the resistor then can be found by taking this voltage that we determined, dividing by the resistance. Similarly, the current through the capacitor as a function of time, we now know can be found by taking v of t, differentiating it, and multiplying that derivative by the value of c. And when you do that, you get that I sub c as a function of t is equal to 0.014 e to the minus 5,000 t minus 0.104 e to the minus 20,000 t. And finally, I sub L of t can be found either by going one, keep in mind that current I in an inductor, when you know the voltage across the inductor is just equal to 1 over L times the integral from 0 to t of v of x dx plus whatever the initial current was, which was 30 milliamps. So if you enjoy integrating, you can integrate this voltage expression using the initial current for that value there. 1 over L times the integral plus I naught will give you the current. Or you can use, again, Kirchhoff's law there, and I sub L of t then would equal negative I sub R of t minus I sub c of t. And when you do that, you'll get the same result as you would have if you would have integrated correctly, and that is equal to negative 0.056 e to the minus 5,000 t plus 0.026 e to the minus 20,000 t. Thus, once you know the voltage across here, you can determine any quantity you want. It's important to note, and let's just take a second to look at these. Here is the voltage. It has e to the minus 5,000 t term. It has a e to the minus 20,000 t term. I sub R, I sub C, and I sub L are all determined from that original expression. Note that each of these currents are of the same form. They each have an e to the minus 5,000 t term. They each have an e to the minus 20,000 t term. The only differences are the values of A1 and A2. In other words, in these circuits, all of the voltages and all the currents in the circuits will be of this same form. The A1 and A2 terms then would simply need to be evaluated from the initial conditions associated with each of those quantities. In general, then, we can say that x as a function of t is equal to a1 e to the s1t plus a2 e to the s2t, where x is any voltage or current we can define in this circuit. They'll all be of the same form. These S1 and S2 quantities are characteristic quantities of the circuit parameters themselves. And keep in mind that we were able to evaluate S1 and S2 from the values of R, L, and C.